Okay, just a little bit. See the slides. Yeah. Okay. Oh, this is the wrong lecture. Don't want to talk about that, right? We can also talk about that if you want. But, okay, so last time I told you that in chemistry we are concerned about changes in matter, right? Structure of matter, and then how this translates into like changes in matter of any form. And I told you that at the core of matter lies atoms, right? And eventually also electrons. And that we can also visualize these things nowadays, which is pretty nice. So we can verify all these concepts. And I told you that all of this has been established over like a long period of time of many experiments. So we will dive a little bit deeper into that scientific method today that led to these discoveries. And I also told you that atoms usually come together to build up molecules. They show a very specific arrangement. So, for example, for water molecule, we have O and 2H atoms, and you may wonder why is it angled like that. And that's something we need to dive deeper in this lecture into. And I already told you that in chemical reactions refer to changes of matter. And on a microscopic scale, we can understand this as rearrangement of these atoms, right? And this rearrangement has to be induced by something, usually some kind of disruption of the system, right? Let's say electric current, or you heat up something, and then some reaction might happen. Okay, so this was the basic thing, and then we started to talk about the scientific method. So the way that we got all this knowledge about atoms and reactions was by a process that involved observation, that involved some new observation to come in to make a new hypothesis, and then making new experiments to prove that hypothesis, and eventually converging into a theory, which can be then used to predict new experiments, right, or new results. And they can be verified by new experiments, and then you can modify the theory if needed. So this is a diagram which pretty well summarizes what people have done without actually knowing the diagram, right? It's just something that human beings generally do if they do research, if they find out new laws in nature. Okay, so steps: make observations. There are qualitative and quantitative observations. Qualitative doesn't involve any numbers. It's basically just something black or white, right? Quantitative means we actually observe a number and a unit. And then formulating hypothesis means we give it a possible explanation. We say, okay, actually now I remember there was one more thing that a student asked me a lot, and I got some emails. What kind of book you should learn with, Korean or English? I mean, all the lecture will be in English, right? So it depends a bit on you. Like if you have like very limited English skills, it might definitely be useful to learn it also in Korean, right? With a Korean book. You just need to make sure that you understand the vocabulary, right? Because in the exam or the short test, all the questions will be in English. So you need to understand the words, right? And the meaning of the question. If you are okay with that, then it's also a good idea to learn with the Korean book if you feel more confident with that. So just use whatever helps you most to understand the topic, I would say. And be sure to understand the questions in the exam. So as I also said, you can answer in the exams in Korean. That's not a problem also. Yeah. Okay. Hypothesis. And then we do experiments to test that hypothesis, which sometimes gather new information. um, to ascertain the validity of the hypothesis. And the best example for that is quantum chemistry, which challenged the view of classical mechanics, right? People always could only observe what happens in the macroscopic scale around us, but when there were experiments available to observe the very tiny particles of nature, then they realized there's something wrong with that theory. It doesn't work anymore. So they made a new hypothesis and they developed a new theory. They updated the theory, which can incorporate all the classical mechanics as well. So the new theory, quantum mechanics, can explain all the limits that we need to describe. And the theory is then the set of tested hypotheses that gives the overall explanation. Okay, and then once you have done many experiments and many theory updates, then at some point you think this is sure, this explains everything we know so far, and then you pose a natural law, which is a summary of all the observed behavior that you have. So you usually combine different theories into one natural law. Example, the law of conservation of mass, which I told you last time. During a chemical reaction, the mass is always conserved. We have the same atoms on all the two sides. And that's an example of many experiments that were done for many different systems, and the theories combined led to this law. So law is a statement on general behavior, yeah, very generalizable. Theory is usually the attempt to explain some specific observation that happened. Yeah, okay. So what is the drawback of this scientific method? Well, focusing on a theory may limit your ability to see alternative explanations, right? So something that you realize, maybe especially if you are along in the business of science, is that you trust what is there, right? So for me personally, I would never try to challenge quantum mechanics, right? But why not? Why not challenging it, right? But because I did so much research and it was always valid, I start to trust a lot that theory, and I start to not have any kind of thought that this might be wrong, right? That's why it is really good to, especially for the young students like you, be critical with respect to everything that people tell you. Of course, there are theories which are well established, like thermodynamics, quantum mechanics, and all of this has been backed up by many experiments, but this doesn't tell you that this will hold true forever. And this also doesn't tell you that this is the best theory to explain everything, right? Maybe someone of you will develop in the future a theory which can much better explain all the observations. And maybe you do an experiment which shows something which is completely against the odds of all this theory, right? So in science, you need to, of course, to some degree, follow what people teach you, like me, but to some degree, always be critical. And I think it's really this criticism that also helps you to learn more. Like you say, okay, well, why is this like this? I don't trust it. And then I ask you, why do you not trust it? Because this and that. And then you will realize, I missed some point, right? Now I understand. Or at some point you say, okay, maybe you're right. Maybe there's a problem with the theory, right? So this is how we talk in science. Like this is how we just keep communicating. That's why there's no dumb question in science. Every question will bring you forward, right? In terms of what you to improve your understanding or to challenge a new theory. Okay, then there's the other aspect that, of course, scientists are human and we have prejudices against the things. And also, of course, science is eventually a business. So I need to be paid as well. So others need to be paid. Everyone who's doing science need to be paid, right? Eventually. So doing science for free is not possible, of course. Everyone needs to survive, right? So all the research funding we apply for is somehow guided by, now for me personally, by the motives of Korea, right? So Korea is investing a lot into quantum computing these days and AI. So if you do these topics, then you're happy, then you can get a lot of funding. But if you don't, then you don't get funding. So many people start to change their topic of interest, of research interest. So the question is this good or not? I don't know, but it will definitely affect the trajectory of science, right? It will bias the trajectory of science towards a certain direction. And that is why I think also thinking against the stream is always really important, because that only can lead to like completely new discoveries. So every Nobel Prize winner you will ask probably was against the stream. Like everyone had problems getting, many Nobel Prize winners had problems getting funding because they were not doing what everyone else was doing. So that is something which is really difficult to do, but they were convinced with some idea, and that eventually led to breakthroughs, right, in science. Okay. By the way, you guys don't need to be here in the lecture. You can leave. You don't need to attend the lecture. Only if the students start to leave, then I will call you back to catch them. But otherwise, you don't need to be here. Okay. So just think about it, right? Like I just said, quantum computing AI, everyone moves to it. Just imagine that every researcher in Korea would start to do that, right? What would happen is that everyone would just follow that mainstream, and nobody would be able to make new discoveries outside of that mainstream, right? Eventually, in science, there's a lot of overlap between different fields, like completely going into other directions can usually help a lot to realize something. Okay, well, this is just something on the sidebar. Now, during this lecture, we will have a lot of these join-ins. Those I see. I mean, I see two of the students. You and you. I think you were in my lecture last semester, so you already know how this works. So I usually will ask a question, and then I will just gather your opinion on that by raising your hand. Yeah. So don't worry. I will not pick someone like that and then ask, why did you choose that? You don't need to worry about that. I just want to gather some kind of rough idea how you can follow the lecture. So these are actually from the book, but I really like it because it really helps me to see if you guys can follow. And sometimes I will just explain a bit more on that. So this is a pretty simple one. Which of these is an example of a quantitative observation? So solution A is darker red color than solution B. So who thinks this is a quantitative observation? Please raise your hand right now. So who thinks this is a qualitative? So that's what I just don't want to see, right? You guys should all raise your hand, either quantitative or qualitative, okay? Everyone, please. So who thinks this is a quantitative observation? Okay, qualitative? Yeah, okay, so most of you. So qualitative doesn't involve any numbers, right? And indeed, this doesn't involve any numbers, it's qualitative. B, the grass is green. Who thinks this is quantitative? Okay, this is right, it's qualitative. C, substance A has a greater mass than substance B. Thinks this is quantitative. Yeah, this is a bit tricky, right? But if you measure the mass, then in order to measure the mass, you need a number, right? But this is still a qualitative statement, right? Because you just say greater than. You don't say the number is this, right? How about the last one? Temperature of water is 45 degrees. Who thinks this is quantitative? Yeah. Okay, so I think everyone understands the concept now. So now, once we do these quantitative measurements, we will get some number, right? And we will also get a unit. And units are really important. Every one of you should be aware of units and should continuously use them, yeah? because units help you also to figure out errors in your equations as well. And they help you to understand equations also as well. So that's why we will spend some time also on looking into units. So there are different kinds of unit systems. There's the English system, which is used in the United States, right? I struggled a lot with over the last month, asking someone what is the temperature, and they always answer me in Fahrenheit. Or with my son having fever, and I didn't know how to, and you always like Google what is the corresponding Fahrenheit temperature. But while they use this system, we cannot do anything against it. But yeah, most people use a metric and SI systems. So we will use also the SI system mostly during this lecture. So here are the SI units for the most important physical properties that we have. Mass, which is measured in kilogram, length in meter, time in seconds, temperature in Kelvin, not degrees Celsius, it's Kelvin. Electric current is an ampere, amount substance in mole, and luminous intensity. I don't know if this is not really important property, I would say. The other ones are quite important. Okay, and then once we have these units, then sometimes we use a prefix in front of that unit because, well, you don't want to always say like 10 to the power of 18 seconds, right? Well, you can just say exasecond. Well, that's a bad example. Let's go in the other direction. You don't want to say 0.00001 seconds, but you can just introduce an abbreviation for that, which you name pico. Pico is 10 to the power of minus 12 seconds. Yeah. So these units are especially important if you go to the microscopic scale. Right? These are important if you go to the macroscopic scale. Like we know about gigaton, gigabyte, terabyte, right? We have all these units here. All these prefixes are from this list, this table. So it's good for you to know how they relate to the exponential notation. And that's something which is good to learn and good to keep in mind for the future, because you will mostly always need these. Okay. So this is just some examples of the units. So you can say a dime is 1 millimeter thick. So here you append the milli, right? 10 to the power of minus 3. And the meter is the unit, SI unit. Quarter is 2.5 centimeter in diameter. Same concept. So I think it's pretty straightforward. You just append that prefix from this list here with the corresponding symbol, and then you can easily like write the numbers and you can convert them into the proper unit. So whenever you do any calculations with this, you need to remove the prefix and then use the standard SI units, right? So you can write like the solution of this task is 0.1 millimeter. This is great. But when you start calculating it and inserting it into your equations, convert to the proper SI unit first, right? So 0.1 millimeter is 10 to the power of minus 4 meter, right? And then you do all your calculations with that. Don't calculate in millimeter, because then the units will not cancel out and you have problems eventually with the calculation, right? So these prefixes are nice for talking to each other and kind of envisioning the numbers without saying too much. But they are quite tricky. They are not so useful if you work with equations, as you will later. Okay, so this is just an example of volume units. So 1 cubic meter can be envisioned as like 10 cross 10 of these cubes. 10 times 10 times 10, so it's 100 cubes. So and then you can basically take one of these cubes, which will be 1 cubic decimeter, right? So because 1 decimeter is 10 to the power minus 1 meter, right? So you get like 1/10 of this, which will be 1 cubic decimeter. 1 decimeter, 1 decimeter, 1 decimeter. And then you take this cube, you can get even smaller, 1/10 of this one. This will be now 1 cubic centimeter, right? And which is 1 millimeter. This helps a little bit to visualize the different volume units. How do you actually measure volume in the laboratory? And you probably learn about this in your general chemistry lab course more. But there are these different kind of things, different instruments you can use. There's a graduated cylinder, there's a pipette that you borrowed, and there's a volumetric flask. And they all have these calibration lines. And the only thing you need to know is that you fill these up, and then until the point that you hit the mark. Very easy stuff. And they have like different uses. So the pipette, as I know, is usually the most accurate. It's usually like for a very specific volume. So it's usually very accurate to measure the volume with that. Okay, how about mass and weight? So mass can be really understood as the resistance of an object to a change in the state of motion. So if you want to accelerate and something holds you back, right, then this is the mass. Right? If I want to jump up in the sky, Earth holds me back, gravitational force holds me back, right? Which eventually relates to my mass. Right? So the unit equation tells you that F equals m times a. This is the mass. So if I want to accelerate, then the mass is eventually what determines my acceleration, holds me back. So the force is the gravitational force. And then for the acceleration, my mass will matter. Right? So that's how we can understand mass. And we can measure it by the force necessary to accelerate. Right? So if I know the force that holds me down, that prevents me from accelerating into the sky, then I can convert this into the mass because I know the acceleration. And then the weight, however, is the force exerted by the gravity of the object. So the weight is directly related. We usually call this directly the force, while the mass is kind of the resistance. Is this property. And the weight varies with the gravitational field. So with A is for the gravitation, this is G, this is the gravitational constant. Yeah, so the weight or the force that pulls me back relates actually also to the gravitational field or the gravitational constant, while the mass is fully a property of myself, right? So the mass is a property of an object. The weight is an effective property in the field of something else, which accelerates. So it's a bit different, so you just need to be careful while talking about this, right? So if you stand on, if somebody weights you, right, how heavy you are, that's ultimately you measure the weight because it's the result of both of these, right? It's the mass of you in the field of the gravitation of Earth, right? That's what we call the weight. Okay. This one I will skip. You will realize I will skip some of these critical figures because some of them I don't find really useful, so I will just skip them, but just feel free to think about it if you want. Okay, so now we have units, we have numbers. Now, numbers that come out of the measurements, they have a certain limit of the numbers we can read from the instrument, right? So just think about a volume measurement. You have like these lines, 1 cubic centimeter, 2 cubic centimeter, right? but how accurately can we give the result of the measurement? Right? That's a very important point, because eventually we will combine different measurements together, and then the question is like, what measurement actually limits the accuracy of our number, of a final number that we have? Right? So for this, you have to think about certain digits versus uncertain digits. Certain digits are the numbers that remain the same regardless of who measures them, which means that it's totally clear to read from the instrument that the volume is 1 cubic centimeter. But it's not so clear if it's 1.1 or 1.2. That's not so clear. So we will not include that in the certain digits. We will include that in the uncertain digits, which must be estimated and will vary. Yeah? And when you report the measurements, then usually you record all the certain digits plus one uncertain digit. So the volume is read at the bottom of the liquid curve, which is the meniscus here. So at this bottom you would read the line here, what is the volume here. And the meniscus in this case of the liquid occurs at 20 here, 20.1. So that's what we can say for sure. It's between 1 and 2, so it should be 21, so 20.1. That's what we can say for sure. But can you say for sure if this is 20.15 or 20.14? Well, we cannot really, right, to be honest, from this measurement. So we will just carry this as the only uncertain digit. So we say this is 20.15, with the last being the uncertain digit. And any measurement will carry this uncertainty. Right? Any instrument will carry a certain precision error. And the significant figures are usually the numbers in which the certainties and the first uncertainties are recorded. This is how we usually call what we usually call the significant figures. And the uncertainty in the last number is usually assumed to be plus minus 1, if not otherwise indicated. Okay, so examples here. So the first number is 9,000. So how many significant figures does this have? So now comes some interesting thing here. So when we write down the significant figures for these numbers, then usually the 0 doesn't count in this case. So we will say the 9 is the only significant figure here. And the 000 will not actually count here, because we will assume that this was anyway rounded to the 9,000. So when we, however, have .00, we will assume that this must not be rounded. The numbers after the point, they must be known, right? Otherwise, why would you write them down, right? If you don't know the numbers after the 0. So we would think that these should all be significant figures. They are important from the measurement. So we would say this has 6 significant figures, right? And by the way, this would be, you can also write it like this, it would be the same thing. Next example, 1.001 has 4 significant figures, right? Same actually as if there would be a 0 in the end, it wouldn't matter. It would also be 4 significant figures. The one more example is the last one. It's 3 significant figures because all the zeros ahead of them, they don't really matter, right? Because you can write this as 3.10 times 10 to the power minus 3. You can see there's 3 significant figures. So basically, if you always use this exponential notation, then you can immediately see the significant figures. Here's 1, here is 6, here is 3. Right? So if you just once figure this out, how to use these significant figures, then it will usually work out. Okay. So now we do some example here. So we analyze a sample of polluted water. And the chemist, he measured out 25 milliliter water sample with a pipette. Is it pipette or pipette? In Germany, of course, we say pipette. Pipette, right? Okay, pipette, sorry for that. With a pipette. At another point in the analysis, the chemist used a gradient cylinder to measure 25 milliliter of the solution. What is the difference between these two measurements, 25.00 milliliter and 25 milliliter? So even though they appear equal, they convey different information, right? Because 25 milliliter means that the uncertain digit is the 5, right? This means that you could only measure it as accurately as between 24 and 26. And that was very inaccurate, I would say, right? Sorry, precise, imprecise. While 25.00 means that the uncertain digit is here. We have 5 significant figures. Sorry, 4 significant digits. So the last one is uncertain, right? So we have like much higher precision in this measurement. Okay, so the pipette measures the volume with a much greater precision than the graduated cylinder. And this is something which I also sometimes do wrongly when I present it so far. I sometimes use the word accurate. But we should be accurate with the definition. So accuracy usually means that we compare to the true value. So we say something is accurate if we think that it is similar to the true value. Precision means the degree of agreement between different measurements. So, for example, if you can measure many significant figures, it's a very precise measurement. Yeah. So the difference, I hope I can keep that in mind, and I also don't confuse that sometimes. But this is the right definition, right? So precision is used when you talk about uncertainty in the measurement. Accuracy is used when you compare to the true value, right? So you can say, for example, this is an accurate approximation if you compare to the true value of the result. Okay, so example here, you throw some dots and you say, okay, the first figure A, this would be neither accurate nor precise. So every measurement, every throw of the dot, we just put it somewhere randomly, and they will not hit the target, which would be accurate because the target is the true value. But they also completely scatter around. So you have like two problems at the same time. For figure B, this one is precise because all the arrows throw at the same point. But it would probably mean that you have some problem with your eyesight. If all your dots, you are a very good dot player, but you don't have that good eyes probably. If you can throw the dots like that, right? So this would be precise but not accurate. The last one is accurate and precise. All the dots throw at the same point. It's a very precise measurement, and it's also accurate because it hits the goal of the true value. Yeah. So I hope that was clear right now. So if these dots or these measurements measure like all kind of different values, they scatter with a certain large arrow, then we call this a random arrow. The measurement that means that the measurement has an equal probability of being low or high. So you throw all your dots and they will just like equally distribute around that point, or usually with a normal distribution. And that occurs in estimating the value of the last digit, the uncertain digit. Right? So the last uncertain digit will be usually like normally distributed around one number. Right? So we call this a random error. So if you ask like 100 students to measure this last uncertain digit, you'll probably see some normal distribution around that one value that people will, on average, agree on. And the systematic error is something different. Systematic error refers to the accuracy of the measurement. It's a problem in the experiment, an approximation that you did that brings you into a wrong result because you designed the experiment wrongly or because your experiment is limited in some sense. Yeah? So these are the two different. So random error refers usually to low precision, while systematic error refers to low accuracy. Yeah. Okay, so the reason why I sometimes confuse these words like precision and accuracy is also because sometimes they are used in the wrong way. And precision is often used as an indication for accuracy. So people do experiments and they show very small random error and they say, oh, it's a very accurate measurement. But we have to be always careful because high precision doesn't indicate high accuracy, right? You have to always differentiate the systematic error of the experiment and the random error. So a small random error doesn't guarantee you that the measurement is showing you the right thing that you want to see. Right? So the assumption of this is usually that when you do many measurements and they are close to each other, they should show the true value, but this is not given necessarily, right? Because of some possible systematic error. Okay, so for example, one of the students now tried to check the accuracy of the gradient cylinder. And for that, he filled the cylinder to the 25 milliliter mark using water delivered from the bird, and then he read the volume delivered. So he uses the cylinder, which is graduated, so which is very precise, and it's also more accurate because it's closer to the real volume. It has been graduated. So he uses that to assess the accuracy of his previous measurement. Right? So you can see that the graduated cylinder always showed 25 milliliter. But when he puts this into the bird, and you can see that there's a scatter around, there's some kind of random error. And the question is there also systematic error on top of the random error? So do you think, who of you thinks that there is a systematic error? No one? Think one more time about it. Well, I already told you the answer. Now everyone will raise their hand. Right? You see that there is a constant deviation, right? Look at this. These are all 25. But 25 was a constant underestimate. All of these are around 1.5 higher, right? This means that there is a systematic error in the previous measurement. It's not just imprecise, it's actually inaccurate. It has a systematic error, right? Okay, so actually the scatter, the random error is not that high, right? If you look at the numbers here, they are very close together, right? So it's pretty the gradient cylinder is pretty precise, but it's not accurate. It has a systematic error. So the student was pretty good in measuring it. The problem was that there was a systematic problem with the gradient cylinder. Maybe there was something down in the cylinder, or it was broken, a crack was there, or something like that. Right? That leads to systematic underestimation or overestimation. Okay, so let's do another join-in. The glassware shown below here, this is called a vart. The vart is filled to the 0 mark at the top here with the solution. And the solution is then transferred to a beaker. What volume of the solution should be reported? 20 milliliter, 22 milliliter, 22.0 milliliter, 22.00 milliliter, or 25 milliliter. You can read this here, right? How much this is. This is white liquid. So what would you report for this? So who thinks it is A 20 milliliter? Who thinks it's B 22 milliliter? Okay. Who thinks it's C 22.0 milliliter? Okay, some hands. Who thinks it's D 22.00 and E 25? So we have like something between B and D, I think, beyond D. So how can you say, like, what are the certain digits here, right? I mean, certain digits are usually the lines that you see, right? So we have like here a line of 20, 21, 22, right? So 22 would be the certain digit, yeah? 2 and 2 is a certain digit. Then the question is how many uncertain digits? And there's actually only usually just one number that we give. We only give one uncertain digit. So the right answer would be C in this case. We would just give 22.0. We just have one uncertain digit, which is the 0 in this case. Okay, and another join-in. The boiling point of a liquid was measured in the lab with the following results. The actual boiling point of the liquid is 28.7. Okay, so you can see the result of the boiling point there. Okay. Now, would you say, okay, I will write the precise one, which is 28.7. Is the, I mean, this is not precise, this is the actual boiling point. So is this determination of the boiling point? Who thinks that this is accurate and precise? Who thinks this is precise but inaccurate? Okay. Who thinks that this is accurate but imprecise? Inaccurate and imprecise. Okay, I think we have an agreement here. Precise but inaccurate. We have a systematic error, right, between those. But all the results are pretty close together, so it's a precise measurement, but it completely fails to give the true answer. Fill this gap and reflects the reproducibility of a given type of measurement. Is it A, accuracy? Is it B, precision? Is it C, certainty? Is it D, systematic error? Is it E, random error? Okay, so I think this is a bit unclear. So what reflects the reproducibility of a given type of measurement? Reproducibility means you do an experiment and you do it another time. The result is a bit different, right? So what is the reason for that difference? Why is it different? What has affected that difference? So who thinks that accuracy affects the difference between different measurements? How about precision? Right, so precision is definitely right? I mean, precision relates to the spread of the measurements across several measurements. How does the number vary when you do another measurement, and so on. Certainty has nothing really to do with this. Systematic error. A systematic error is something that doesn't really affect your reproducibility. It's something that will give you a constant shift of all your results from the true value, right? It has nothing to do with reproducibility. And random error also actually has to do with it. Random error has to do with the precision as well. So also that will affect the reproducibility. Okay. Is the agreement of a particular value with the true value? Who thinks this is A, accuracy? Okay, I think that will be our God. We can continue here. The problem is, of course, in reality, you don't know the true value. That's the point of doing the measurement, right? You do the experiment because you don't know the true value. So who tells you what is the true value? Well, no one. That's the point. So you need to just do like different experiments to increase your trust in that theory, in that measurement, right? And if different experiments can confirm the same result, then this usually increases the trust that your measurement is accurate. Like completely different experiment, independent experiment, different setups, right? But in generally, we cannot really know if the experiment is accurate or not if we don't know the true answer. Okay, so I already told you a little bit about the counting of the significant figures. So I showed you some examples already, but let me also go into these rules a little bit more detail. So non-zero integers are always counted as significant figures. And the zeros, we need to distinguish them between the leading zeros in the beginning, the captive zeros, which are between two numbers, which are non-zero, and the trailing zeros. So I'll give you an example here. Okay, so these here are the leading zeros. These are captive, and these are trailing. And we need to distinguish in how we treat these different zeros. So let's look at this first. So for the leading zeros, we usually don't count them, as we said, because typically, yeah, we can write it in the exponential notation like this, right? So everything which goes before in front then doesn't really matter, like for the number itself. I will just write x here. They don't count. For captive zeros, we always count them for the significant figures because obviously they are measured, right? They're in between actual numbers, so they definitely are measured. For the trailing zeros, they are significant only if the number contains a decimal point. Right? So in this case, they would be significant. We would count them. But for the other example which I showed you, like this, right? And this would be the trailing zeros. And in this case, they would not. This is two significant figures. Because it's clearly rounded, we think that this is a rounded number. So we would not count them towards the significant figures. But this is a bit different to the certain uncertain digit, right? If we measure this number and we note it like this, still this is the certain digit and this is the uncertain digit, right? But for significant figures, we will only count these two. So it's a bit different between significant and certain digits, and not always the same. So that's something you need to just keep in mind. Okay. Actually, this one, I forgot to remove this. I had this 2 times. Oh, okay. Okay. What's the time? Actually, we did already 1 hour, so maybe we can stop for today. That's the first lecture. I don't need to like overwhelm you. We will continue with this discussion next week, Tuesday. And I will upload this video in the Dropbox. If anyone had problems with the Dropbox link, then please let me know. Thanks. Tuesday, but not next week after. From next week. From Tuesday. Yeah. Yeah. Every Tuesday from the week after next week. The short is 10 minutes. I don't know. You can see on the slide, in the beginning, I have this overview of the lecture times. So here is the final exam and the midterm. Oh, I forgot to write midterm here. Okay, I realize this now. I will change this one here. This is the midterm exam.
What time would this be?
That will be during lecture time.
Lecture time.
Yes.
Only that.
Only lecture time. Only 1 hour 15.
Oh, okay.
Yeah. We do it shortly, but intense.
It will be tough.
Thank you. Yeah, thanks.
Professor, could you please explain the definition of reproducibility?
Yeah, it just means that you do an experiment again and you get a different number. This exactly same experiment is set up, exactly same experiment. You do it again, but the number is different. You do it another time, number is again different. And you get some kind of scatter around some.
But like
this. So you get, sometimes you get 22.0, 22.1, there's some kind of random error, right? So yeah, that means it is, well, in this case, the error is very small. So we would say it's reproducible. But if one measurement gives you 22.0, the other one gives you 23.5, the other one gives you 20.2, and I would say it's not reproducible because the random error is too large. It's not really a precise measurement. That's what we usually do. That's actually a very important reproducible thing. Always when you do experiments, you should make sure that your result can be reproduced by a follow-up experiment on another day, maybe in winter, in summer, different temperature. That's sometimes very critical. Yeah. Mm-hmm.